Hello everyone. So today I will introduce you the first uh, JPEG, real JPEG steganography technique, which can be used in practice. So compared to the previous example where we just hide data into the JPEG coefficient, that just gave us the way access to the specific room in the JPEG image where the data hiding is possible. But in the general steganography, we will have to keep a few different interesting components in our mind. The first of all, JPEG or any kind of steganography is the secure way of hiding data. So without checking the security, data hiding cannot be called as the steganography. So we must check security of the data hiding method. So if that checking procedure is failing using the modern steganalysis technique, so we can say that this technique is not secure enough to be used nowadays. Okay, so what we are going to discuss today is like the general JPEG compression. So technically we already discussed it before, so but here is just some kind of overview. So from the original bitmap image, so we can read data, we can read 8 by 8 blocks. For the each 8 by 8 blocks, which is displayed here, we will process discrete cosine transformation. So after DCT, the coefficient, the block of the coefficient looks like this. So we need to quantize that particular block of coefficient using the quantization table, which is standard for JPEG. So that's why we can just keep using those coefficients for the all 8 by 8 blocks taken from the image. So by processing that quantization, so finally we will have that block of coefficients where most of the coefficients are 0 and just some of them are not. So, and those non-zero coefficients we will use for data hiding. So based on the general JPEG procedure, we cannot use 0 for data hiding. So we must use only non-zero coefficients. At the same time, we already discussed that. So DC coefficient, that top coefficient here, we cannot use for data hiding as well. So that's why the next what we will need to do is to handle that particular coefficients. And most of the JPEG images after compression, they giving us that particular table. In the previous lecture, so we use those non-zero coefficients for data hiding. Okay, so where is the steganography steganalysis here? So how does it work? So assume that we want to send some information from point A to the point B, and I want to send it secretly and by using some certain JPEG steganography technique. So we are taking the image, hide our data into the JPEG image using the JPEG steganography. So here we are using the encoder. So that particular data will be embedded into the image, and that particular image will be sent through the internet to the receiver. Receiver can get this data, can read the image and get the data. So encoder, decoder for sure must be designed in respect of each other. So that should be one technique using the one protocol or some certain protocol for the encoder and decoder in one single framework. Okay, at the same time, adversary, as long as they can get access to the internet, so they may try to process the JPEG steganalysis. By analyzing all images circulating in the internet, adversary can analyze all images what I circulate in the internet And by using the advanced analysis technique, can distinguish in between original and stego. So that actually prompt the designer, so this person who is doing the steganography, uh, design the data hiding JPEG steganography technique such that adversary will always fail to make a difference between original and stego. So the method what we discussed before will definitely fail against any kind of stego analysis because we did not even consider so that the adversary will try to analyze our images. So and definitely here, so we will need to like set up some technique so which can be used to prevent JPEG stego analysis. Uh, okay, so how it can be done like in details? So today we are going to discuss the matrix encoding technique. So for the matrix encoding technique, is based on the very famous Hamming code designed for the error correction. So in these lectures we will not cover the error correction, so the main ideas of the matrix encoding came from the error correction coding. So the first we will need to define the matrix encoding size. So according to the matrix encoding rules, I can hide n bits of data into the block of the 2n minus 1 coefficients. The coefficients here, that will be the non-zero density coefficients, like similar to what we do have here. Here there are a few examples of the Hamming code, like 2, 3. So I can hide 2 bits into the 3 coefficients. One important notice here, I can hide that particular data by modifying only one single coefficient. So for example, I can hide 3 bits of data into the 7 coefficient. So I will flip only one coefficient among 7 coefficient, and I will hide 3 bits of data. So compared to the technique what we used before, where the one coefficient we used to hide 1 bit of data, efficiency of this technique is 3 times higher. So I can hide 3 bits and flip only one. But for that, I need more number of coefficients, 7. Remember in the previous case, our like data hiding ability was just 10,000 bits from, like, if I'm not mistaken, 400 coefficients. So definitely, so we don't really need all of those 400,000 in order to hide just like 100,000 bits. But by using the Hamming code, so we can occupy more available coefficients and hide and use only few of them. So again, this is the point of using Hamming code and the matrix encoding. So and according to this equation, so the scheme can be even different, like 415 and so on. So now, how does it work? The first of all, we need to get the string of the non-zero coefficient, like this. Okay, so after that, from each coefficient, so we can recover the bit, like corresponding bit, in respect of the coefficient magnitude. So the equation how to get those kind of informative bits is given here. So technically, this is the simple modulo 2 operation. So the important part here is the negative numbers, because if our coefficient is negative, so I will process the modulo 2 in respect of the coefficient minus 1. So we are doing that in order to prevent artificial number of 1, because coefficient 1 and minus 1 will give us modulo 2 equal 1, which is wrong because the number of 1 and minus 1 in the JPEG image is much bigger compared to all other coefficients. So at the end, if we will calculate the number of all 1 and all 0 in our informative bit, if I'm not using this equation for the negative part, so will be different, will not be the similar. So in reality, if we want to keep the statistical properties into our image, so the number of 0 and number of 1 in terms of our coefficients must be keep similar, not same, but keep similar. So if will be the difference in between number of 0 and number of 1, that will automatically means that there is something wrong with our image, and the steg analysis will definitely detect that something is going on. Okay, so once we got those coefficients, so the next will be to define the matrix encoding scheme. So it depends what message size I have, and depends how many coefficients is available. So we will have to process data hiding based on that equation. So we will need to identify how many blocks, how many bits I need to hide in each block in order to satisfy the maximum biggest block for data hiding. So and in that equation, so n, this is the number of non-zero coefficient. So n, this is the parameter from our matrix encoding. C, this is the message size, the number of bits what I want to hide into the image. Okay, and here this is the data hiding scheme itself. So, and the example here is that according to the previous calculation, assume that the matrix encoding scheme is 3, 7. So means that into the 7 coefficients, I want to hide 3 bits of message by modifying just one coefficient. Okay, so the data will be 0, 0, 1, the data what I want to hide. Okay, assume that my coefficient is this. So after processing recovering those informative bits, so I can get that particular set of bits. Okay, done. So, and now what do I need to do is to find the position of the coefficient in between those 7 coefficients. The coefficient, what do I need to flip? So that position will be written in the binary form, P1, P2, P3. Okay, so now how does it work? We are using something that's called the parity check matrix from the Hamming code, and that matrix is given here. So in order to calculate, in order to get our position, so the first what we need to do is to calculate something that's called the syndrome. Syndrome also has the 3-bit in turn if we are using the matrix encoding 3-7, O1, O2, and O3. So how to get our data from here? Very easily. So as long as the coefficients are given, A1, A2, A3, A3, so we already have those coefficients. In order to calculate O0, I will need to XOR elements 4, 5, 6, 7. So those elements we can get from that matrix. 1, 2, 3, 4, 5, 7. Okay, 4, 5, 6, 7. 4, 5, 6, 7. So those the one link to the XOR numbers in order to calculate the different O. So in order O1 will be the XOR based on the one in that particular parity check matrix. So for the O2, that will be the A2, 3, 6, 7. O3, that will be 1, 3, 5, 7. So we can get different bits. Okay, and finally the binary position P can be calculated as the XOR in between our syndrome O, which again 3 bits of data, and our message M, which is 0, 0, 1 in that particular example. And that's all for the technique what we are going to discuss today. So in here there is an example, like the complete example taken from the previous case. So 1 0 0 1 1 0 0. This is our like informative bits. Syndrome will be calculated as 0 0 0. Got like, get it? So and now how to get position? So I supposed to process the XOR in between my message and syndrome, and we can get 0 0 1. So the 0 0 1. This is nothing else as 1. So and now in order to get a modified stream of data, so my first coefficient must change that 1 to 0. So and there are two ways to do that kind of modification. So I can either move that coefficient 3 into the 2 or 4, because modulo 2 over 3 is 1, but modulo 2 over 2 or 4 will be 0. And that's what we need to do. So after changing that particular coefficient to 2 or 4, so finally we can get the 0 here, and we can also process the verification. So if my first coefficient will be 0, if I will process exactly the same calculation here, I can get my message. So 0 0 1, so that will be the message what we wanted to hide in the beginning. So means like we succeeded. So here we calculate all necessary things for the matrix encoding and finally hide our data into the image. Okay, so today our target will be to hide the secret message what we designed for the last lecture for the general LSB steganography, and hide that particular hello student binary message into the test image, and make sure that we can read that message back and finally complete the coding. So now let's code everything what we just discussed here. So let's make a new one. So here that will be matrix encoding. Encoder. So like most of the operations, so we can get from our previous code, removing data, okay, data size, okay, up to the data hiding, I think we can do. Okay, so the negative we also need. Yeah, let's copy up to this part. So the first of all, let's read our image. Okay, so what I will do, let's make the folder images, because I will always move it here. Record data. So and that particular path. So let's add here. So we will read stego image and stego data. So remember the stego data is our hello student binary file. So at the final stage, we must get those hello student data. If everything is going right, so we will see that particular image. Okay, so now what is going on inside of our source code? So as I said, everything will be pretty much same. So here we remove our DC coefficients. Okay, process the reshape. Remove all of the non-zero coefficients, like remove all zero coefficients, get only non-zero coefficients. So read our data, reshape that data, no problem, exactly the same. Okay, and now data hiding part. So for the data hiding part, so see here, the number of coefficients what I need for data hiding is not really clear. Because remember, according to the data hiding, so the first what we will need to do is to define the data hiding scheme. So data hiding scheme. So that we need to process, like first get our binary coefficients, and after that get the necessary matrix encoding scheme. So okay, let's process that. So this is our original LSB. So but here those LSB we will need to process in the double format. So see here it is modulo 2 if positive, and C minus 1, coefficient minus 1 modulo 2 if negative. Okay, so this is our, should be MZ here. MZ, so and original LSB, where my non-zero coefficients is less than 0, will be modulo 2, and here also negative. Okay, so what does it mean? So the first of the original LSB will be the same as before, so it means the modulo 2 over the all coefficients including negative. But now the all negative coefficients, so I will process as those coefficients minus 1 modulo 2. That will give us exactly the same numbers. So what is presented in the slides. And let's check whenever it is true or not. Okay, so here the problem is that in the folder we're supposed to place a test image. So image security, images, we are using test image. This is our original JPEG image, what we will use for data hiding. Okay. So this is our original LSB. So altogether 400,000, like briefly 400,000 coefficients and 400,000 informative bits. So here important part will be to see negative coefficients. So now let's see, does the negative convert it correctly or not? Okay, see, 13 is odd 1, so minus 2 minus 22 is even, so it must be 0, but that became 1. That's correct. So because we process like minus 1, minus 16 1, 12 1, minus 4 1, okay, 0 1, 0 0, minus 6 1. Okay, we need odd negative to see whenever it is working well or not. Let's go for twins. Okay, see, minus 33, minus 23, 0 0. Yeah, that works. Minus 9, 0. So everything is fine. So the next what we need to do is to define block size using this equation. So what is our n? So n, this is the number of nz coefficients. So n, that will be the size of y and z 2. So we already know this is the 430,115. Okay, so next, what is C? C, this is our message size. Message size. And we already know, because this is our data size. So this I can rename to C. Okay, so the rest, so we can calculate. Let's calculate n, and let's calculate C. So n, C. Okay, so data is given. Now we need to use that particular equation to get the number, necessary n. So remember, according to the inequality, that particular number n divided by 2n minus 1 multiply n must be bigger than c. Okay, so n, let's make n from the bigger. Yeah, we can try both way anyway, like 20 until 5. Minus 1. Minus 1. Now, what will be the block size? 2 power n minus 1. So that will be the block size. And okay, 20 is too much. This is 1 million. We do have only 400,000. I think better to split n 15. Okay, so this is our n, 2 power n. Okay, now n divided by 2 power n. Okay, dot. Interesting. So, okay, so what is this? N divided by the 2n minus 1. So that will be the number of blocks for different n. If I will divide the number of coefficients by the size of the block, I will define the number of blocks. So n divided by the 2n minus 1, where the n is not fixed value, will give us the number of blocks. So now if I will calculate that particular number by n, so that will be our message size. Okay, and now let's say when it is bigger than C. here. That the first one, that will means our necessary n. Okay, and what I will do, let's change n from 1 to 15. Maybe better 2. Let's process. Okay, see here 1, 1, 1, 1, 1, 1, 1. So that will give us like 7. Let's check. N 1, 2, 3, 4, 5, 6, 7, 8, 7, 7. So now let's take this. For example, I will place 0. And let's say n0 equal 8. So what will happen? So and if I will get 9. So what does it mean? So if my n is 8, I need so the message what I can hide is 129 12,980 960 coefficients. Okay, so if my n is 9, so the number of hidden bits will be 7,276. But again, I need 10,824. So means that I must use n equal 8, this one. Okay, so now I need to like systemize the case. So let's do this. Get the coupler n. Okay. Let's use n0. Later I can modify. So and process this. What can I do? I can just calculate the sum. So I had 7, 1, but my number was 8 because I started from 2. So here I need to add 1. So that will be my n. Okay, and let's do it. Okay. 0 n. Okay, bigger than C. 8. Okay, so the scheme is fixed. So we got that for our, according to the message and according to the image we have, n must be 8. So 2 power 8 minus 1, 255, that will be our block size. So the each block, so here in example we had like 7 bits. In our case that will be 255 bits, and in each block we will hide 8 bits of data. So we will need to identify that particular position of the block, what we will need to calculate. Okay, so the next what we will need to do is to divide our image into the blocks. But the first, let's define how many coefficients we need. So now I can calculate n of blocks, isn't it? So the n of blocks will be that number. So the n divide, okay, and I think we made one simple mistake. Okay, see this number, that will be the float number because we are dividing by something. Okay, so here better to do the seal. So in here we can get the decimal numbers. Yeah, that it is still. So n will be still 8, but okay, so here the number of blocks, better to keep this seal. And not this. The number of blocks we will have to calculate using the C. Okay, see, my C is the 10,824. Okay, now, what if I will divide the C by 2 power n minus 1? So that will be the 42. So means that I need 42.44 blocks. But the number of all blocks what I have in the image, this is the 1620. So the altogether our image has 1620 blocks. Actually, here maybe better to do this seal. 61, 1621. So in our case, if this is the 42, so better to have like one block more, like 43. So and now let's do this also sale 43. So that will be the number of blocks. So technically that number I supposed to place here. So actually you can try with the n equal 9 to see how many blocks will we have. But we already identified that the message size will be smaller. That's why we must use n equal 8. Okay, this is the 43, and now see. This 43. So in order to get the total message size, I'm supposed to multiply by n. Okay. Okay, my bad. No. See, here I'm supposed to divide by n. Yeah, that one. This is correct. N I supposed to divide by 2 power n minus 1, so here that should be n. So that will be our number of blocks. Okay, so now it is correct. 1353. So now if I will multiply that number by n, so I will get 10,824. See, my C so they divisible each other. So we got very lucky. So in many cases, C cannot be easily divided by n. So for that, we will need to do the padding. So, but sometimes, very rarely, we may have that situation. See, the number of blocks is exactly match with our message. Okay. So assume that this is working. So we do have the number of blocks. So and now we can divide. So we can identify how many coefficients I need like to process my data hiding. So altogether 413,000. So let's call it like y use. So that will be y and z from 1 until what? So I already know how many blocks I have. So here will be number of blocks multiply by the block size. So the block size, this is a 2 power n minus 1. And what I want to do here, let's identify the block size because we will use it very often in our source code. So and here I will just multiply by the block size. So once again, the block size in my code block size 255. Number of blocks 1353. So and the total number of coefficients what I need is 345,015. Okay, done. So the next what I will need to do is to reshape that y use. Yeah. Y use reshape. Why? Because we will use blocks of the coefficients. So the later. And how can I sort them? Like how can I reshape them? So the block size over the number of blocks. So I will have the matrix. So where we can place, like this is our matrix. So here will be 255. So here will be 1,353. 53. Okay, so that will be our matrix. So first, that will be our block 1. So here will be the block 2. So here will be the block 3 and so on. Okay, so the same I will need to do with the binary coefficients. So original LSB I have. So let's make the original LSB use original LSB this part. Okay, and let's reshape. So the size of them is the same as the size reshape. Will be the same as the size of our coefficients. Okay, that is finished. So the next what we are going to do is to calculate syndrome. So those coefficients we already have that numbers. So they will be located in our original LSB use. So the next what I will need to do is to calculate the syndrome. So actually now we start processing the general data hiding because here I need a loop from first block until the number of blocks, and okay, so and here it's yeah, I can use the same S, so that will be our original LSB. Okay, so OI, so that should be our 255 bits. So now how to calculate syndrome? So in order to calculate syndrome, I need to know the matrix H. So means that yeah, okay. Okay, so get proper n. Let's make create matrix H. How can I create matrix H? So in order to create matrix H, I need n, so which we already calculate, and for different n I can define. See here n is 3, isn't it? How to get this matrix? 0, 0, 1, this is binary 1. 0, 1, 0, this is the binary 2. 0, 1, 1, this is the binary 3. 1, 0, 0, 4, 5, 6, 7. So this is the way how to get this matrix H. Okay, let's try this matrix. I need some number, let's say f, from 1 to 7. Okay, now let's convert it into the binary. This to bin f. And now we can see 0, 0, 1, 0, 1, 0, and all of them, but this is the char. So let's make it double. Minus 48. And reverse. And now we can get our parity check matrix. So here our H will be this. So but here instead of this F, which was 1 to 7, so here I supposed to do this 1 to n. Block size. Block size. Okay. And let's see. Look. Or not. H8 over the 255. Well, let's see. Yeah, looks okay. This is our matrix H. So now what I need to do in order to get each of my syndrome, I'm supposed to process the XOR operation. So how can we do this? So yeah, let's stop here. This is my bits, 255 bits. And I do have my matrix H. Okay, so now let's try to multiply by S. Okay, so how does the matrix multiplication works? So here, everywhere where I do have 1, so I will connect with the different coefficients. So technically, only if I do have 2, 1, like 1 in the message, 1 in the parity check bits, I will get the 1 because of the XOR part. So see here, if I do have coefficient 1s, like 1, So the XOR in between those two one, like technically I will need to count how many of them I have. So if that number is odd, that will be 1. So if that number is even, that will be 0. So in our case, as long as I am doing the general multiplication between H and S, so here every time when I do have like 1, 1, so that coefficient will be will be used. So the all other coefficients like they will be rejected. So and finally that should be something like this, modular 2. So that will be our original message. So the message, what like the syndrome that 0, 0, what we got here. Okay, so like we will check so that part as well. So that will be our syndrome. I can call it O as well. So this number, and now what I need to do is to create the message. See, in this example, I need the message 001, where I can get it. So in our case, I do have like data row. So what was calculated in the beginning. So actually what I can do, I can also reshape my data row based on the case what I need, isn't it? So reshape, so and I can get the message for hiding. So data row, so here that will be n and number of blocks. So that will be like 8 over the 1353. So means that my message so will be nothing else as this data row I. Okay, done. So this is our O. Okay, the syndrome. So that will be the XOR. XOR. So in between O and message. Like O message. Let's see. Syndrome 0, 1, 0, 0, 0, 1. Okay, so we got it. So and see now I supposed to get the decimal number. So my XOR is 0, 0, 1 in that example. So and decimal number will be 1. So this is our syndrome 0, 1, 0, 0, 0, 0, 1. So how can I get the original number? So technically what we can do, as long as I already know my n, so I can power my n. Okay, so here will be n minus 1, 1. Okay, 256, yeah, true. Okay, n minus 1. Should be n minus 1. Okay, here that should be to 0. That should be 8 bits. Yeah, 8 bits. Done. So and that particular set of numbers I can multiply by my syndrome. Okay, and now do the summation. And 65. So that is the coefficient what I need to flip in order to get my hidden bit. So the message what I want to hide is 01. Yeah. All of our messages will be like this. Okay. 65. Position. So now let's try. So S. This is my S. Okay, so here in the position is 1. So means that that coefficient I need to change to what? So if this is 1, I will need to change to 0. If this is 0, I need to change to 1. So S pos plus 1 modulo 2. So how does it work? So if my coefficient is 1 plus 1, this is 2 modulo 2, 0. So if my coefficient 0, 0 plus 1, 1 modulo 2, 1. So that operation will flip my coefficient. So here, flip coefficient. So we flipped our coefficient. Okay, and now let's verify. So did I process my data hiding correct or not? So if I flip my S, so what kind of effect? So it will give us later. So because after flipping multiplication, so this multiplication should give us the hidden message 001. So our message is all 1, so we will have to get it here. Okay, so if I will now multiply, so here instead of O, I will get hidden message. Hidden message is all 1. So if it is all 1, this is our message. It means that our data hiding has been processed correctly. Okay, so and I will need to do it for the all blocks. So for each block, I will need to identify the position and hide necessary data. Altogether, there are 1,353 blocks. Okay, this is all perfect. So, but this certain way of flipping the bit doesn't really change my coefficient, because I will need to change my coefficient as well. Okay, so and now, so in here, we don't really need verification. Okay, so here modify JPEG coefficient. So here in the position, I So, and now this is what. And here, where is the trick? See, in the original situation, so we do have two choices. It is either 2 or 4. So, but if we have a coefficient 1 or minus 1, so I cannot process like move from 1 to 0 because that will be the 0 coefficient. And in the decoder, I will need to skip it. So that's why if I do have coefficient 1, I have only one move from 1 to 2. The same way, if I do have minus 1 and I want to hide that data, so the coefficient must change from minus 1 into the minus 2. It cannot go to the 0 as well, similar to what we have for the positive coefficients. So, and that's why here we will need to check. So if so this coefficient is bigger than 0, so I will do +1. Else -1. So if my coefficient positive, I will add 1. So it means that even if I will have 1, that will always go 2. And all other positive coefficients will always move into the positive part. So in case of the negative coefficients, so I will do the same, but my -2 will always go into the minus. -1 will always go into the -2, will never go to the 0, and all other negative coefficients will just increase the magnitude. So and finally that will be the effect of the modification. So technically we finish with data hiding. And the next what we will need to do is to rebuild our JPEG image by using this use_rs where the coefficient has been modified. So what do we need to do? Okay, so later we may need it. Okay, so here let's recover JPEG image. So the very similar way we process in the previous case when we use the LSB steganography. So the first what I need to do is to get the original set of coefficients. Okay, after the reshape. Let's call it like Y mod because they are modified. So Y mod. So here will be the Y use reshape. So and here the size should be 1. Size block size multiply number of blocks. So that will be our Y mod. Okay, see here the Y mod so that was the part of our Y and Z. Okay, so and what we can do, our Y and Z mod will be the Y and Z. So and so the portion of it so will become Y mod. So we are taking those modified coefficient Y mod, what we process here, and place them in our Y mod, Y and Z mod. So okay, we need this because we didn't modify the all coefficients from the image, and we still have significant portion of the coefficients which was untouched by our data hiding technique. Okay, so the next, what we need to do, okay, I think I can go encoder and just get all of this data back. Okay, so now we need to add okay, so one step left. So here we need to add a non-zero coefficients of this part. So the reshape mode, so that will be our the image size. So the image size, yeah, we have. Okay, so after that, so everywhere where we do have non-zero coefficients, so we will place our non-zero coefficients. Okay, add the DC coefficient from Y original, modified our structure, and finally finish it. Okay, so here instead of the stego image, let's write like stego, like matrix encoding. Stego matrix encoding. Okay, and okay, so and here we definitely will have some issues. See, sometimes I cannot do that. The first of all, let's display where it cannot process 211. So here, if I equal 211, stop. Okay, we got position 0. What's happened? See, my syndrome is all 1. Message is all 1. So what will happen if the message and syndrome getting same? So means that we don't need to modify any coefficients. Those modification is already processed. We don't need to do anything. So our original message, actually our original coefficient has the same hidden bit what we want to hide. So we don't need to modify anything else. So when our position is 0, so I don't need to modify. So means that if our position like is not equal 0, I will process my data hiding. So if it is 0 means like first of all like I cannot process this line because Matlab cannot get access when the position is 0. So and if we will consider that, so everything will work well. So position not equal 0, process. Okay, so here there is some error. Y mod is not Y. Okay, Y and Z. interesting. Okay, so here instead of Y mode, we need to use this YRS mode. Okay, so okay, so actually the problem is here. See, I will do the reshape back first. I call it different. So RS mode. Okay, okay, RS mode. Yeah, so now that should work. Okay, done. So this is our stego image. So right here, this hello students binary message is hidden. So now our target is to read that particular message. So for that, I will use our previous decoder because so decoder here will have like all necessary data what we need to recover. Okay, so here let's make a new one. 5, save as matrix encoding decoder. So stego matrix encoding. And the path is different. Path is different and the image. Okay. Remove DC, recover data. Yeah, that part. So here we will need to add some metrics in coding decoder. So how can I process the data? See here, this n, so that tell us how many coefficients do I need to read from the message, like from the original image, because that will identify the how big, what portion of the coefficients did I modify. So in our case here, the parameter what I need to send to the decoder will be different because I also need to verify so the size of my modified coefficients. So, but as long as we use the matrix encoding, so here what do I need to do is to know the n. Instead of the capital N, I need to know n. N is 8. So we use 8 in order to hide data. See the size 1, size 2 here, that will identify our message size, isn't it? So here, for example, how can I get the message size? So that will be my size 1 multiply size 2. So, and the total, that should be that 10,000. So now I can calculate the number of blocks. So that number of blocks will be the message size divided by n, isn't it? Okay, so now the block size. So the block size. So the block size will be exactly the same as we had in the encoder. Okay, done. So now I will need to process all of my coefficients in the similar manner what I did in the decoder. So now, so that part I will need to recalculate now because n z bot. So here will be not n. So here will be what? Number of blocks multiply block size. So that will occupy exactly the same amount of coefficients what I had in the beginning. Okay, now I don't need that coefficient as well. So I need the binary data from them. So here we use the original LSB. So, but here we need it. So those informative bits. So how we can call it? Not original LSB. Let's call it like modified LSB. So that will be our YREC. So and we can read the negative coefficient as well. So and now those modified coefficients, remember here we reshape them. So I will need to do those kind of reshaping also. So modified LSB. Reshape. Block size and block. Okay, let's check. Okay, works. So now for the each of those blocks, we will need to process that calculation. Yeah, for sure, we will not need all of them. For example, those as modified. So that will be our modified LSBRS. So the message I will need to calculate. So in here, this instead of this O, that will be our hidden message. H S mode. So and hidden message actually I can build as the two-dimensional matrix. So in here that will be what n number of blocks. Okay, remember here in the encoder, so when we process this, so row like data row rs, that was like n again, and the number of blocks. So in the decoder we can did the same. So and now the message will be what? So here I will add that message one by one into my matrix hidden message. Let's call it like reshaped, because this is reshaped. Just for instance, let's add it everywhere. So in that part, definitely we don't need. Okay, so we don't have H. Let's add this part. Size block. Okay, this is our hidden message. So after that, we will need to reshape our message. So actually, we will need to reshape it twice here. So reshape message res1. So in here, that will be our block size multiply stop and blocks m multiply n blocks. Okay, and after that we will reshape it again in order to get data original. Okay, let's run. Show data original. Yeah. Hello students. So finally, so we did it. So what is happening here? So we used technically old but very interesting matrix encoding idea, matrix encoding data hiding scheme, so which was very popular in the JPEG steganography. So we utilized that particular idea, create the source code in Matlab, and finally we hide that information into the image. So that's all what we need. So with the all details, so technically we succeeded. And also remember, so here that image has our hidden like hello student binary image inside. So and we did it using the Hamming code based matrix encoding. Okay, that's all for today. Good luck.